Swayam Prabha. Digital India. Educated India.
Horizontal alignment part 5. In lesson 3.10, we have discussed about various basic elements and terminologies related to transition control. We have discussed the need or advantages for providing transition curve, what are the advantages if transition curve is provided, and also the basis for using spiral transition curve. Why spiral curve is used in horizontal alignment. We have also discussed the Indian Roads Congress approach for design of length of transition curve. So, all these aspects we have discussed in lesson 3.10. After completing this lesson, the student will be able to understand the AASHTO approach, American Association of State Highway and Transport Officials, AASHTO approach for transition design control, considering both tangent to curve transition and also spiral curve transition. In tangent to curve transition, no transition curve is used. We have a tangent and then a circular curve directly. For spiral curve transition, a transition curve which is basically a spiral curve that is used in between the tangent and the circular curve. So, under both cases we shall discuss about the AASHTO recommendations and approach for transition design control. Now, let us again touch these two terminologies, tangent runout and super elevation runoff. We have discussed these things earlier, but again we shall talk about these two items. Tangent runout is basically the length of roadway needed to accomplish a change in outside lane cross slope from normal cross slope rate to 0. So, basically if we take a normal cross section, a cambered cross section, it looks like this. Okay. So, from this position we want to get it like this, if the rotation is with respect to center line, a position like this. So, from A to B, this is achieved over a length, and from B to final super elevation, this is achieved, say with respect to the rotation about the center line. So, to attain the full super elevation. So, from B to C. So, A to B, this portion is known as tangent run out, okay, outside cross slope from normal cross slope rate to 0. So, this is the normal cross slope to rate 0 because it is flat outer edge. And super elevation runoff is the length of roadway needed to accomplish a change in outside lane cross slope from 0 to full super elevation. This is 0 and this is the full super elevated cross slope. So, from B to C. So, the length which is required to change the cross section from B to C, that is known as super elevation runoff. Now, let us also see this sketch, the typical diagram, whatever we have discussed now. So, this is the normal cross section at this point. Now, from A, this is earlier A to B. So, this length is actually known as tangent run out, and then from this cross slope to the required cross slope for super elevation, say this is C. So, this is again achieved over a length. So, that is known as super elevation runoff. Here the rotation is with respect to center line. Now, as I indicated, we shall discuss the transition control for tangent to curve transition as well as for spiral curve transition. Let us talk first about the tangent to curve transition. Now, tangent to curve transition, two elements are important for us. One is the length of super elevation runoff, and then second item the length of tangent runout. Now, let us see first the length of super elevation runoff for tangent to curve transition. Let us look at these items. Considering the appearance and comfort, considering appearance and comfort, there should be a maximum acceptable difference between the longitudinal grades of the axis of rotation and the edge of the pavement. Nearly a similar aspect we have discussed when we discussed the Indian Roads Congress approach for determining the length of transition curve. So, there should be a maximum acceptable difference considering the appearance and comfort. Now, in IRC, a single value was recommended for a given terrain condition. It was 1 in 150. In this case, there are two recommendations. The relative gradient is recognized as a function of design speed. So, it is not same rate or same relative gradient that is used. This relative gradient varies with design speed to provide longer runoff lengths at higher speed and shorter length at lower speed. So, relative gradient is not a fixed quantity, this is a function of the design speed. Accordingly, different values of relative gradients have been suggested in AASHTO guideline. Ranging from design speed 20 to 130. Accordingly, maximum relative gradients are 0.8 for 20 km per hour design speed and 0.35 for 130 km per hour design speed. Now, the corresponding equivalent maximum relative slopes are 1 is to 125 and 1 is to 286. That means, for higher speed and lower speed, maximum relative gradient and the equivalent maximum relative slope, these values are different. Now, limiting these two values, that means for 20 and for 130, for intermediate speeds, the value of maximum relative gradient or equivalent maximum relative slope, these values are interpolated from 0.8 to 0.35. Similarly, 1 is to 125 to 1 is to 286. Say for example, for a value of 50 km per hour, maximum relative gradient becomes 0.65 and the corresponding equivalent maximum relative slope is 1 is to 150. You may recall our discussion about Indian Roads Congress provision for design of length of transition curve. The rate recommended for plain and rolling terrain is 1 is to 150. So, that means that is basically corresponds to 50 kilometer design speed. But IRC does not change this value of relative slope depending on speed, but AASHTO recommends different value of maximum relative gradient or equivalent maximum relative slope as a function of design speed. So, accordingly these values are to be taken for design purpose. Intermediate values are also given by interpolating these two extreme values, and those are given in AASHTO guideline. Now, considering these aspects, the minimum length of runoff is decided using this formula. This is the equation what is used, LR equal to W n 1 into E d by delta multiplied by B w. Now, let us try to understand this equation first, excluding this term B w. That means, initially without considering B w. Now, W is the width of one traffic lane expressed in meter. Now, N 1 is the number of lanes rotated. So, if we consider a 2-lane road and the rotation is with respect to the center line, then N 1 is 1. Similarly, if it is a 4-lane undivided road and the rotation is with respect to the central line, then N 1 equal to 2. If it is a 6-lane divided road and the rotation is with respect to the central line, then the value of N 1 is 3. So, accordingly W n 1 gives us the total lane width that is going to be rotated. This term is multiplied by E d. E d is nothing but the design super elevation rate in percentage. So, what it gives us basically, suppose if this is the rotation with respect to central line, say this is the central line, then this gives us W n 1 into E d gives us this distance. Okay. Now, this is the W n 1 and E d is the design super elevation rate. Now, this much change to be achieved over a length with delta maximum relative gradient. So, delta is the maximum relative gradient. So, what is the length required? Length required would be then W n 1 into E d by delta. So, that much length will be required to achieve this required super elevation with maximum relative gradient. Now, if we use only this part of the equation, then whatever will be the length, required length for a 2-lane divided road rotated with respect to center line, the requirement for a 4-lane undivided road, all are undivided road. So, 2-lane undivided road and again 4-lane undivided road with respect to again rotation with respect to center line, the required length in the second case will be twice the length required in the first case. Similarly, if we consider a 6-lane undivided road, all are undivided road, let us consider 6-lane undivided road, the required length will be 3 times than what was the requirement for a 2-lane undivided road. So, it will be just proportional to the number of lanes rotated. Now, practically or say from theoretical point of view, that much length may be desirable, but it may not be practical to consider that much requirement of length. So, therefore, this value B w is used to adjust this length requirement. So, B w is multiplied, which is known as adjustment factor for number of lanes rotated. So, therefore, this B values are B w values or this factor is suggested. AASHTO guidelines again give us or indicate the factors for different number of lanes rotated starting from 1, 1.5, 2, 2.5, 3, 3.5 like that. Say for 1 adjustment factor is 1. So, length increase relative to 1 lane rotated is also 1, there is no change, but as the number of lanes rotated is increasing, say for 3, this B w factor is suggested as 0.67. So, actual length increase relative to 1 lane rotated becomes 2. That means, for 3 lanes rotated, the length is not 3 times as compared to the first case here, but it is basically 2 times. So, therefore, runoff lengths are basically adjusted downward. This is important. The runoff lengths are adjusted downward on a purely empirical basis to avoid excessive lengths for multi-lane highways. So, to avoid excessive lengths for multi-lane highways, this factor B w adjustment factor is used to have downward adjustment in road length, runoff length, and to avoid excessive lengths for multi-lane highways. Now, that is about the runoff length, what should be the length of runoff. Now, the other component for tangent to curve transition, what will be the length of tangent runout. Now, tangent runout, the length will depend on what is the normal cross slope that is to be removed, because if you remember correctly, the tangent runout length is required to have a cross section from the normal cambered section to the outer edge which is flat. So, that means how much crown or how much negative slope is to be removed, number 1, and at which rate it is to be removed. So, these are the two principal considerations that will decide the length of tangent runout. Now, that relative gradient whatever is used, it is same as whatever is used for the calculation of super elevation runoff. So, that means for super elevation runoff, whatever relative gradient is used, the same amount of relative gradient is used for the calculation of tangent runout, and considering similar triangles, this calculation can be done. So, let us see, as I indicated, minimum length of tangent runout, it depends on amount of adverse cross slope that is to be removed, and also number 2, the rate at which it is removed. So, now the rate, as far as the rate is concerned, this relative gradient used is same as whatever is used for super elevation runoff. So, look at this sketch now. If LR is the length of runoff that is required to achieve design super elevation ED, then to remove this normal cross slope ENC indicated here, this is the normal outer edge position, whatever length is required, that is nothing but the tangent runout. So, LT is ENC by ED multiplied by LR. This is basically the same relative gradient is used. One can also consider this, these are the two similar triangles, this is one and this is another one. Okay. So, if this is the length required for ED design super elevation, then whatever is the length required for or to remove this normal cross slope, that length is decided, that is LT. So, that way one can calculate the minimum length of tangent runout. Now, for two aspects we have discussed, minimum runoff length and minimum runout length. Now, both aspects or both minimum runoff length and runout length, predominantly they are a function of the design speed. So, for different design speed values can be estimated 20 km per hour to 130 km per hour, and also it depends on the maximum super elevation rate. Starting from 2%, it goes up to 12%, because H2 allows maximum super elevation rate up to 12%. So, 2%, 4, 6, 8, 10 and 12. Now, for all these conditions, depending on speed number 1, depending on maximum super elevation that is permissible, the value of minimum runoff length and the runout that can be estimated. So, those values are estimated and given in tabular form. So, one can pick up the appropriate value from the table. All these values are given in AASHTO guideline. Now, location with respect to the end of curve. Remember that we are discussing super elevation runoff length for a situation which is tangent to curve transition. That means, there is no transition curve or spiral curve in between the tangent and the circular curve. So, now the question comes, we know what is the length of super elevation runoff. Should we provide the whole super elevation runoff length on the tangent portion itself, or we provide the whole super elevation runoff length on the circular curve portion? Now, for tangent portion, actually the radius is infinity, and as such there is no need of super elevation. So, if we provide the complete super elevation on tangent, then that super elevation may not be necessary at all, considering the radius and considering the movement on tangent portion. However, if we start introducing the super elevation from tangent portion onwards, then the super elevation runoff length completely comes on the circular curve portion. Then once the vehicle enters into circular curve portion, the required super elevation corresponding to the radius of curve for the circular curve portion will not be available to vehicles. So, that again is not desirable. So, it is neither preferable to have the complete runoff length on tangent, nor it is required or nor it is desirable to have the complete runoff length on the circular curve portion. Both have their own disadvantages. So, what is normally done or what is normally preferable is to divide runoff lengths between tangent and the curve section to minimize the peak lateral acceleration and the resulting side friction demand. That is what is indicated. So, divide the runoff length between the tangent and curve section instead of providing the whole runoff length either on tangent or on curve section, and this is done to minimize the peak lateral acceleration and the resulting side friction demand. Then immediately the question comes, at what proportion? How much then on tangent and how much on the circular curve portion? Yes, many agencies they actually follow different standards, different proportions. It varies from 0.6 to 0.8 on the tangent portion. That means 60 to 80% of the runoff length is provided on the tangent portion itself. It varies from 60 to 80, that means the 0.6 to 0.8, that is the factor. And a large number of agencies they are using 0.67, which is nothing but 2/3. So, 2/3 of the super elevation runoff length on tangent and the remaining 1/3 on circular curve. Now, here we can refer back or we can recall our discussions about the Indian Roads Congress specification, where I have mentioned that as per IRC the distribution what is recommended is 2/3 1/3, that means 67% and 33%. So, again there is a similarity, then there is a kind of compatibility between AASHTO recommendations and the recommendations given by the Indian Roads Congress. So, it may vary from 0.6 to 0.8, and a large number of organizations they are actually using a single value which is 0.67. Now, from theoretical considerations, that means this peak lateral acceleration and other things, and also considering the driver behavior. So, one is the theoretical consideration, the other aspect is the driver behavior. Now, I have mentioned it earlier also, the natural path of driving is spiral. So, therefore, and that itself follows a transition curve. So, even if no transition curve is present in reality, the natural path of driving is transition, and more specifically it is spiral transition. So, considering this theoretical aspect and considering the natural path of driving, it is desirable to place a longer proportion of the runoff length on the tangent portion itself. So, that is what is indicated here. larger portion of the runoff length on the tangent portion is desirable from theoretical consideration and also from the consideration of driver behavior. Accordingly, AASHTO suggests the portion of runoff length located prior to curve or on tangent portion, making it a function of the design speed range. One is used as 20 to 70 kilometer per hour, another is in the range of 80 to 130 kilometer per hour. So, we can say lower speed range this one and 80 to 130 they may be used for higher speed range, and also it depends on the number of lanes rotated. So, making it a function of the design speed range and the number of lanes rotated, the portion of runoff length which is to be located on the tangent portion is decided, and that proportion varies from 0.7 to 0.9, 0.7 to 0.9, and accordingly for different number of lanes rotated 1.5, then 2 to 2.5, these values are suggested, intermediate values are suggested. All these values are available in AASHTO guidelines. I have indicated a few values just to indicate the trend or explain the trend. Now, with all this, if we again look at the existing practice, that means most of the agencies or a large number of agencies at least, they are using 60 to 80% super elevation runoff length on tangent portion, and a large number of agencies they are actually using 0.67, that means 2/3 of the total super elevation runoff length on tangent portion. If we look at the existing practice in the light of this theoretical considerations or the values which are recommended by AASHTO guideline, and as I have indicated a few minutes back, it is found that a minor variation, say 10% variation, does not really affect the overall operation to that extent. That means, existing practice indicates that 10% variation does not lead to major operational problem, Therefore, although these are recommended as I have shown here in tabular form, a single value say 0.67 may also be adopted. However, wherever situation permits, wherever condition permits, a more refined design standard may be adopted as indicated in this table. Okay? That means, different proportion depending on the number of lanes rotated and also depending on the design speed range. So, that is a more refined design consideration, but a single value is also acceptable. Now, so that completes our discussion about tangent to curve transition. We have discussed what should be the minimum length of super elevation runoff, what should be the minimum length of tangent runout, and the location, how to distribute the super elevation runoff length between the tangent length and also the length of the circular curve. Now, let us talk about the spiral curve transition. Now, in spiral curve transition, two aspects are generally considered, and whatever lengths are calculated based on two different aspects, the larger value is accepted as the minimum required length of spiral curve. First criteria is based on driver comfort, and the second one is based on the lateral shift. Now, this first criteria based on driver's compute, it is similar to what we have already discussed when we discussed about the Indian Roads Congress provision, a maximum value of the rate of change of centrifugal acceleration. So, if length is known, velocity is known, then what is the time taken to cover the length of transition curve? Now, the maximum lateral acceleration v square by r is introduced in that time. So, what is the lateral acceleration that can be estimated, and accordingly we calculated the required length of the transition curve. The same basis is used here. So, let us look at the formula. It is 0.0214 VQ by RC. L is the required length of transition curve, V is the design speed in kilometer per hour, R is the radius of circular curve in meter, and C is the maximum rate of change of lateral acceleration. So, the basic formulation, this equation what I am showing here, this is similar to what was discussed and what was mentioned when we talked about the IRC recommendations. Only thing the difference, the value was 0.0215 VQ by RC, and here it is 0.0214 VQ by RC. That is the only difference, but basically it is the same equation. Now, the difference is basically in the consideration of C, that is the maximum rate of change of lateral acceleration. In Indian Roads Congress guideline, an empirical formula was suggested for the calculation of the design C value, and also there was an upper limit, a lower limit also. C was recommended to be between 0.5 to 0.8, although there was an empirical equation formula for the calculation of C, but this lower and upper limit also should be checked as per IRC, and that value was 0.5 to 0.8, in between 0.5 and 0.8. In this case, as per AASHTO, the value what is normally used as 1.2 meter per second cube. So, that is what is a major difference. In IRC it was 0.5 to 0.8, if I remember correctly. This value was 0.5 to 0.8. In this case 1.2 meter per second cube is allowed. So, that is the value of C what is normally used. Of course, there are many agencies which are using a value other than 1.2, lesser values are also used. Sometimes values in this range 0.5 to 0.8 is also used by many agencies. So, this is also used, but a recommended value is 1.2 meter per second cube. Now, the other consideration is based on lateral shift. This was not covered when we discussed about the Indian Roads Congress provision. Now, this is basically to ensure that a spiral curve is sufficiently long to provide a shift in a vehicle's lateral position within its lane that is consistent with that produced by vehicle's natural spiral path. So, vehicle they take a natural spiral path, that is the normal behavior. So, considering the vehicle's natural path, we are considering this lateral shift as a criteria to ensure that spiral curve length is sufficiently long to provide a shift in a vehicle's lateral position within its length. That means, it does not encroach, so that it does not encroach the adjacent length within its length that is consistent with that produced by vehicle's natural path. Now, while talking about this spiral curve and its different properties, we gave a formulation how to calculate the shift. That shift was calculated using the formula Ls square by 24 r. This was mentioned in lesson 3.10. Using the same basis, we are now actually calculating the required minimum length for a given design value of P minimum. So, this is the formula what is used. Ls minimum is root over 24 P minimum multiplied by r, and the value of P minimum, that is minimum lateral offset between the tangent and the circular curve, that is used for design purpose. The value used is 0.2 meter. So, 0.2 meter value is taken for design for the calculation of minimum length of spiral, considering the lateral shift and to ensure that a spiral curve is sufficiently long to provide a shift in a vehicle's lateral position within its lane that is consistent with what produced by vehicle's natural spiral path. Now, it may be mentioned here that the value, design value of 0.2 meter, what is taken as the value for P minimum, it is consistent with the minimum lateral shift. This value of P minimum as 0.2 meter is consistent with the minimum lateral shift that occurs as a result of natural steering behavior of most drivers, not all drivers, but most drivers. Considering most drivers, whatever is the minimum lateral shift, I would put emphasis on this part, minimum lateral shift. So, it is consistent with the minimum lateral shift that occurs as a result of natural steering behavior of most drivers. Then we can get a value of Ls minimum. Now, considering both these aspects, that means considering the driver comfort, we calculate the length of curve, considering the lateral shift, we calculate the length of curve, and whatever gives us the higher value, that is to be taken as the minimum acceptable length of spiral. Now, a relook at super elevation runoff and length of spiral. Now, super elevation runoff is provided based on relative gradient, we have discussed it already. So, super elevation runoff is calculated based on relative gradient. Length of spiral is calculated based on driver comfort and lateral shift. Now, wherever there is a spiral curve transition, the super elevation runoff is accomplished over the length of transition curve. That means, super elevation runoff is accomplished over the length of transition curve. Now, this raises a question, that means there is a necessity that length of spiral and super elevation runoff, they must be compatible to each other. A compatibility is required, because for spiral curve transition, the super elevation runoff is accomplished over the length of transition curve. Now, in general, the calculated values for length of spiral and length of runoff do not differ materially, they are nearly same in most of the cases. However, as both of them are calculated using empirical basis or in view of empirical nature of calculation, it is desirable to have an adjustment in one to avoid having two separate sets of design criteria. That means, basis for super elevation runoff calculation and basis for length of spiral calculation, they are not same, they are different. And we are saying for spiral curve transition, super elevation runoff is accomplished over the length of transition curve. So, there has to be a compatibility between the two. Most of the cases they are not different, but because they are basically empirical in nature the calculation, therefore, it is better to have an adjustment in one to avoid having two separate sets of design criteria. Now, the length of run up applicable is applicable for all super elevated curves, whether it is spiral transition or it is tangent to curve transition. In both cases it is valid. Therefore, what is recommended normally is the length of spiral should be set equal to the length of runoff. I repeat this part, the length of spiral should be set equal to the length of runoff, then there will not be any compatibility problem. So, two different design criteria will not appear, there will be overall compatibility. Now, obviously, before we do that, the change in adverse cross slope is done by providing tangent run out, and the change in adverse cross slope begins by introducing a tangent run out section just in advance of the spiral curve, and in following this design standard wherever we are using spiral transition and following this basis, the whole of the circular curve will have full super elevation. The whole of the circular curve will have full super elevation. Now, there is also a provision for maximum length of spiral. Why it is so? We have discussed about the minimum required length of spiral. What happens if we provide a longer length? Let us stretch ourselves, our thinking, if we provide a very long length, okay, there are problems, and that is what indicates the need for deciding a maximum length of spiral. Now, there could be safety problems on spiral curves that are very long relative to the length of circular curve. So, we are talking about conditions where spiral curves are there, but length of the spiral curve lengths are very long as compared to the length of the circular curve. Now, what is the problem? Why we are talking that there could be safety problems? Because under those conditions, drivers or those conditions may mislead the driver about the sharpness of the approaching curve, approaching circular curve, because circular curve have a designated radius, and if the transition length is too long, then that may mislead the driver about the sharpness of the approaching curve, and eventually there could be safety problem. So, again a maximum length is suggested using this formula. It is already the basis is known, but here it is LS max instead of LS minimum, and the P instead of P minimum it is P max. Equation is same, and P max is nothing but the maximum lateral offset between the curve and the tangent. In earlier case, when we are calculating the minimum length, this was minimum lateral shift between the curve and tangent. This case it is maximum lateral shift between the curve and the tangent, and for design purpose the value is taken as 1 meter. Now, here also P max as 1 meter is consistent with the maximum lateral shift. In earlier cases, when we talked about the LS minimum considering the lateral shift, there the recommended value of P minimum was based on minimum lateral shift that occurs. In this case, it is based on the maximum lateral shift that occurs as a result of natural steering behavior of most drivers, and it also provides this P as P max as 1.0 meter. It also provides a reasonable balance between the spiral length and curve radius. So, that gives us, so this equation will give us a maximum limit of the spiral length. Now, there is something called desirable length of spiral. So, we have talked about minimum, maximum, now it is the desirable length of spiral. Now, why this desirable length? Most desirable operating conditions are where spiral curve length approximately equals to the natural spiral path adopted by drivers. I have indicated it a number of times that the driver's natural driving path is also spiral. So, one is whatever is the driver's natural paths per spiral and the length, and whatever is the spiral length that we are providing for the design purpose. If both these things are matching, that is the most desirable operating condition. Now, difference between these two lengths may result in operational problems associated with large lateral velocities or shift in lateral position at the end of transition curve. That is what tells us the problem. So, most desirable condition is spiral curve length equal to the length of natural spiral path adopted by the drivers, that is the desirable spiral length. And AASHTO recommends that a length corresponding to 2 seconds travel at the design speed of the roadway will generally give the desirable length of spiral. So, desirable length of spiral is 2 seconds travel at design speed of the roadway, and whatever length is covered in 2 seconds time at design speed, that will give us the desirable length of spiral. Now, if we use the longer lengths which is less than maximum length of spiral, then it is fine, it is acceptable. However, where such spiral are used, travelled way should be widened adequately to minimize the potential for encroachment into adjacent lanes. So, longer lengths are fine, but adequate widening should be done. If desirable spiral length is less than minimum spiral length, then minimum spiral length curve should be used in design. So, whatever we are saying desirable length, that is to be checked against the minimum required length, and minimum required length must be satisfied. Now, let me put some questions. Explain the basis for obtaining the minimum length of superelevation runoff as per AASHTO procedure. Number 2, explain the basis for calculation of the minimum length of spiral transition curves, again as per AASHTO recommendations or AASHTO approach. And third, explain the significance of considering an upper limit for the length of spiral. Why an upper limit is suggested in AASHTO design guideline. Try to answer to these questions. Now, let me try to answer the questions of lesson 3.10. The first question was, what are the advantages of providing transition curve in horizontal alignment? There are several advantages. Number 1, it helps us to introduce gradually the centrifugal force between the tangent point and the beginning of the circular curve, avoiding any sudden jerk on the vehicle. Number 2, enables driver to turn steering gradually with comfort and safety, that means it gives easy to follow path for drivers. 3, minimize encroachment on adjoining traffic lanes and tend to promote uniformity in speed. 4, enabling gradual introduction of design superelevation that is super elevation runoff, particularly this length, and also enable gradual introduction of required extra widening. Finally, it improves the aesthetic appearance of the roads. So, those are all the advantages of using transition curve. Now, why spiral is used as an ideal shape of transition curve in horizontal alignment? Because for ideal shape, rate of introduction of centrifugal force or rate of change of centrifugal acceleration should be consistent, which means that the length should be inversely proportional to radius. Now, if we look at the spiral, for spiral radius is inversely proportional to the length, and the rate of change of centrifugal acceleration is uniform throughout the length of the curve. That means, which tells us that spiral fulfills the condition of an ideal transition curve. Moreover, the geometric property of spiral is such that the calculations and sitting out the curve in the field is simple and easy, because the equation is simple, LR equal to constant. Also, spiral transition curve simulates the natural turning path of a vehicle, a very important consideration. Therefore, spiral is used as an ideal transition curve. Now, explain the basis for calculation of the length of horizontal curve as per IRC. One is based on the rate of change of centrifugal acceleration, which gives us this basis Ls equal to 0.0215 V q by CR. We have also discussed this basis today, and IRC gives this empirical formula C equal to 80 by 75 plus V, where C is in meter per second cube and V is in kilometer per hour. So, that gives us the design value of C, and it is to be checked against the lowest and highest value, that is 0.5 and 0.8. And also based on the change of super elevation, the rate of change suggested are 1 in 150 for plain and rolling terrain and 1 in 60 for mountainous and steep terrain. So, considering these two, the higher values to be adopted. Also based on the second consideration, the rate of introduction of super elevation, IRC suggests two empirical formula, one for plain terrain and one for mountainous and steep terrain. So, these empirical formulas are also sometimes used as a alternative to the second criteria, because it is basically coming from the same basis. Now, let us also quickly see how these empirical formulas are derived. If E is the maximum super elevation, W is the carriageway, W is the extra widening, then the total raise of pavement with respect to center line is E into W into WE divided by 2. Why divided by 2? Because rotation is with respect to center line. Therefore, for 2-lane carriageway, it is assumed that the carriageway is 2-lane with the 7 meter, extra widening is 0.9 meter. So, E max is 7%, accordingly total raise is 0.2675. So, N 1 in 150 means 42 meter length. Now, because LR is constant, radius of the curvature at point where maximum super elevation is obtained is 0.0635 V square. This is obtained considering 75% of the design speed IRC provision. So, V square by 225 R equal to V square by 225 R. So, R is V square by 225 into E. This E value is 7%. So, that means Ls into RC equal to this one and Ls equal to 2.67 V square by RC. So, you must be careful when you are using this empirical formula, because lot of assumptions are involved and has gone inside it. Thank you.